All right, so let's try the next algorithm. We did linear search, we did binary search, so we're done searching for now. On sorting, the first one we're going to talk about is selection sort. So let me get this list of numbers here. That didn't work. There we go. Okay, so the way selection sort works is, I just realized that I usually, I don't think I want the big thick borders here. Let's do if I do this, will it change it? Nope. No, I guess this is fine. All right, so the way selection sort works is this. Find the smallest, or select the smallest item in the portion of the array that has not yet been sorted. Swap that item with the first item in the portion of the array that has not yet been sorted. Okay, the complicated part of that sentence was the portion of the array that has not yet been sorted, right? But I think you'll see what I mean as we do it. So smallest number is 15, right? So I'm going to swap the 15 with the 82. This stuff over here, I'm just going to get rid of. Okay, so just swap the 15 and the 82. Okay, and I'm going to highlight this cell to say that portion of the array has been sorted. Okay, so select, I'm using the word select because so you get the idea, that's where it gets its name, right? Select the smallest item that's left, that would be the 35, swap it with the first element in that portion of the array that has not yet been sorted, so that would be the 55. Swap the 55 and the 35. Swap the 55 and the 35. Boom. And now that has been sorted. Okay, keep doing the same thing. Smallest item is 38, so swap the 38 with the 92. Let me know if you want me to slow down. I kind of wanted to actually complete the whole thing. It was probably not necessary, but so I'm going to just kind of go fast, but let me know if that's a bad thing. What's next? 43. Swap the 43 and the 67. Now that's sorted. Now the smallest is 55, so swap the 55 and the 90.
There's a 53.
Oh, thank you. Swap the 53 and the 90. Now that's sorted. Now I get to do the 55 and the 92. And now that's sorted. Now I get to do 60 and 82. Now I'm going to do 67 and 90. Now I'm going to do 82 and 96. Almost done. Now I'm going to do 90 and 92. Now I'm going to do 92 and 92. And now I'm done. I don't need to do that last one because there's only one item left. So it's automatically the biggest item. Okay. Everybody can do that on your own. Like if I gave you 12 numbers right now, you could sit down on a piece of paper and work that out. Okay. All right, let's talk about big O. I'll give you this isn't really a hint, I guess, but it's just an observation. You can sort of tell just by looking at how many numbers I typed on the screen what the big O is going to be. But basically, here's what we're doing. How many times did I have to look through the array? N, right? Now, to be technical, it's n minus 1, right? But we don't really care. N's close enough. Or we can keep it at n minus 1 for now for our conversation, either way. So we're going to, whatever this process is, we're doing it. We had to do it n times. How many comparisons do we have to make on each of those passes? Worst case scenario. N, right? I mean, you might be thinking, okay, well, you know, on this second to last one, we didn't have to do n, we only had to do 2, right? But it's still a function of n. The number of items that we're having to look at each time for each of these steps is a function of n. On average, it's n over 2, right? In the worst case, it's n. We're going to just call it n. So we have to do something n times, and that something requires n comparisons. So how many comparisons are there? N squared, right? That makes sense. Now, just to be clear, I'm being a little bit loose here, right? I said that big O is a function of how many operations an algorithm requires. And I'm sort of shedding all of the peripheral stuff, and I'm just focusing on how many comparisons there's going to be, because that's the part that depends on n, right? Or n squared to be precise. But so I switched my terminology. Instead of saying how many operations are there, I'm saying how many comparisons are there, because that's what matters to us. Okay, so selection sort, big O, n squared. Okay. Any questions on that?
Isn't that pretty inefficient?
That's extremely inefficient, yes. Very simple algorithm. Writing the code is pretty straightforward compared to some of the more efficient algorithms that we're going to see on Wednesday, I guess. Okay. So as far as code goes, I'm trying to decide which version to do. Let's look at this. So there's a selection sort. If you had me for A or B, I did a selection sort in the lesson on arrays. So you could go look at that. And in that version, I actually split out the finding the smallest item into a separate function, which makes the code clearer, but it actually ends up making it quite a bit less efficient. So in this program where I'm actually timing things, I kept it all in one function. So this should not be that hard to figure out. Let's look at it. I've got a for loop that's going from 0 to enum items minus 1. That means each time through this for loop, I'm finding the smallest item and swapping it to the front. And I'm doing it num items minus 1 times. That's what we did in the Excel spreadsheet, right? Okay, so each time through the for loop, what I'm doing is I've got this loop that is just finding the index of the smallest item. Start off by saying the index of the smallest item is I, because that's the first, I represents the first element of the portion of the array that has not yet been sorted, right? Go through the rest of the elements in the array, and if I find one smaller than list subindex of smallest, now the index of the smallest is that new index. So find the smallest index of the smallest, swap it to the front. That's all there is to it. Questions about that? Okay. And as you can see, you can get to this code from the lesson. Okay, how are we doing? All right. I think we can do bubble sort.